What is the total electric force on the -2 nanocoulomb charge? Okay, step one. I'm gonna figure out which charge we're talking about here. I want to know the total electric force on the 2 nanocoulomb charge. Just like in our other problem, I'm going to put a box around the charge that I'm trying to learn things about. Okay, trying to figure things out about. Then, just like the problem before that had two charges and we're trying to find the net electric force, okay, we are going to find the force between the 4 and the 2. We're going to find the force between the 2 and the 7, and then we're going to add those vectors together. So, first, let's go ahead and find the force on the 2 nanocoulomb charge by the 4 nanocoulomb charge. Okay, remember, we have Coulomb's constant times the first charge, in this case charge 2, times the second charge, charge 4, divided by the distance between them squared. So we can substitute in 8.99 times 10 to the 9th for Coulomb's constant, times 2, and it's 2 nanocoulombs, so that's times 10 to the -9th, times 4 nanocoulombs, so times 10 to the -9th. And we're not putting the negative in here because we're going to leave the negatives, just tell us which direction we're going, if they're attracted or repelled, and then from there we can determine which direction things are going. Divided by the distance between them. Well, it's 0.12 millimeters. Okay? Well, millimeters means 10 to the -3rd, so I need to move the decimal place 3 spots to the left. It's actually going to be 0.00012 squared. Type that into our calculator, and we get it's a 4.99 Newton force on charge 2. Now we need to decide the direction. Well, this is where the negatives come into play. This is a -4 nanocoulombs. This is a -2 nanocoulombs. All right. Like charges repel each other, so this is going to feel a force going up, and our charge we're worried about is going to feel its force going down. Okay, so 4.99 newtons in the downward direction. Okay, so we've got the force on charge 2 by charge 4. Next, we're going to find the force on charge 2 by charge 7. So again, Coulomb's constant times the first charge, which is charge 2, times the second charge, which is charge 7, divided by the distance between the two squared. Start substituting in. Coulomb's constant times 2 times 10 to the -9th times 7 times 10 to the -9th divided by, and now we have to be a little careful. We need the distance between the two. Well, that is this distance, which is not labeled. Okay, however, you'll notice we have a right triangle up here. So we can use Pythagorean theorem, a squared plus b squared equals c squared. So one leg has 0.00012 meters. The other one, again, 3 spaces to the left. So 0.00005 squared equals c squared. If we solve, we are going to find that the distance between the two is 0.00013, or 13 millimeters. 0.013. Don't forget to square the distance. Type that into our calculator, and we get it is a 7 45 newtons force acting on charge 2 by charge 7. We're missing something, the direction again. Again, we have to come look and decide. Well, this is a -2 nanocoulombs. This is a +7 nanocoulombs. Opposites attract, so they're going to be attracted to each other, which means the charge we're worried about is going to go up and to the right. Of course, we need to know a little bit more about that than just up and to the right. We want to find that angle. So what angle is this? Well, in order to figure that out, we're going to use some trigonometry. So we're going to look at to find this angle right here. Okay, so let's go ahead and change our color a little bit. So we're trying to find theta right here. So I want to use a little trig. So I'm going to say opposite and adjacent. I'm going to use the tangent function. I'm going to say the tangent of this angle right here, theta, is equal to the opposite side, which I just covered up, but it said 0.00005, okay, over the adjacent 0.00012. Now to solve this, I have to do the inverse tangent to both sides. Cancels tangent and inverse tangent cancel on the left. And then I'm going to be left with 22 and 6/10 degrees for my angle. So we can put that up here. And that is this angle. Draw that in. Okay, now I have the two forces, but we want to find the overall net force. So I need to add them together. Well, in order to add them together, this one's pretty easy, it's straight down, but this one's at an angle. So I'm going to figure out what are the components of that. How much of that's going up and how much of that is going to the right. So to do that, I'm going to draw this vector. Okay, and it's 7.45 newtons. And the angle was 22.6 degrees with this vertical. And now I'm going to find the missing sides. I'm going to call this side F parallel, and I'll call this side F perpendicular. So the parallel component, the perpendicular component. So here's my angle. That means that this side is the opposite and that this side is the adjacent. So let's go ahead and find the opposite first. So I want to find the opposite, and I know the hypotenuse, so I'm going to use the function sine. So the sine of the angle, in this case 22.6, is equal to the opposite, which is the parallel component, divided by the hypotenuse, 7.45 newtons. And in that case, we find the parallel component is 2.86 newtons, and that is going to be going to the right. Similarly, we can find the perpendicular. Well, that's the adjacent, and I still know the hypotenuse, so I can use cosine. So the cosine of 22.6 is equal to the adjacent, which is the perpendicular component, over the hypotenuse, 7 45/100. Solve this, and we will find the perpendicular component is 6 88/100 newtons, and this is going up. I want to find the overall net force on this, so I want to add this vector to this vector. Now I just broke it down into its components, so I'm going to kind of ignore that one now that I've got the components. I'm going to add the top vector plus the two components for the bottom vector. Okay. So first we're going to figure out what's the net force in the x direction. Well, if I go over here and look, this one's down, that's the y direction. This one's up, that's the y direction. I only have one force in the x direction, and that is the 2 86/100 newtons to the right. So that's all the force we've got in the x direction. Next, we're going to find the net force in the y direction. So we're going to combine. We've got 4.99 newtons down, so I'm going to make that negative. So we talked about forces, down was negative, plus 6.88 newtons, and that's up, so we'll let that be positive, which means overall, the net force in the y direction is 1.89 newtons, and since it's positive, it is in the upward direction. And now I get to add these two vectors together. Remember, we go tip to tail, so I'm going to take 2.86 newtons to the right, and then add the other vector of 1.89 newtons up, and I'm going to add the two vectors together, I'll get that, which is the hypotenuse, okay, which is my net force on charge 2. So I'll go ahead and use Pythagorean theorem. So 2.86 squared plus 1.89 squared is equal to the net force on charge 2 squared. Solve this. We get 11.75 is equal to the net force on charge 2 squared. Take the square root. The net force on charge 2 is 3.43 newtons. And again, we've got up and to the right, but we want an angle. So we need to find this angle, theta. So to find theta, we're going to use some trigonometry again. Okay, so this is the opposite and adjacent, so I can use tangent. So the tangent of the angle is equal to the opposite, 1.89, over the adjacent, 2.86. Take the inverse from both sides, and we get 33.46 degrees. Oops. So our answer is the net force on charge 2 is 3.43 newtons at an angle of 33.46 degrees, and we need to draw the angle in our picture so that we know which angle of the triangle we are talking about.